Now let's deal with this delta H, okay? Now delta H is a bit weird, and that's what this second diagram is for, okay? At the moment, unfortunately, precisely because I have made this slice as infinitesimally thin as I can on my diagram, I can't really work out what this distance is. So on this second diagram, I want us to imagine if we actually blew out delta H so it was big. Okay, we don't want it to be big, but if it's big, we can actually work with it and try and understand the geometry behind this. Okay, so here's what I'm going to do. Remember, we have this point A, so I'm just going to stick it over here, say, xy. That delta H, it's actually the distance of a little chord. So I want to make that chord a bit bigger, right? If it's a chord, that means it joins 2 points on the circumference, right? So I've got one of them already, I just need another one. Let's call it B. Okay. Now, this is interesting. I could have gone up the circle, or I could have gone down the circle. Doesn't matter all that much. Now that I've got B, right, the whole idea is that it's a little distance away from A. A small distance. Now, going along this axis, I'm calling that delta H. But here I need some coordinates, right? I need some coordinates. So I need an X and a Y that are a little bit away from A, which is xy. So I'll give you the easy one first. This B point, it's clearly higher than A, right? So it's like the y coordinate plus a little extra y, right? Well, I already have language from when I talk about a little bit extra on a certain axis. I'm going to call that y plus delta y. Okay, just go up a little bit. Okay? Now, it's a bit unusual to start with the y's. The reason why is because going from A to B, I'm going up. So that's why I add delta y. But when I go from A to B on this particular configuration, which way do I go for x? Answer to the left, right? So in fact, this is not x plus delta x, unless I want delta x to be negative, but that's just confusing. I'm just going to say it's x take away a little bit. I'm going to the left, okay? I have to because I'm still on the circumference of the circle. Okay, now this is pretty much all we need. I want you to see, where would delta h be on this diagram? If that's where A and B are, which are kind of like the top and bottom of my, bottom and top of my little infinitesimally thin cylinder, okay? These things are going to extend to be perpendicular to my axis of rotation, yes? And what I've done is, that's part of the cross section. That area is the bit that's being rotated around to give me my cylinder. Do you agree with that? So then, when you look at this thing, the delta H that I'm after is actually here. Do you see it? It's this distance along this axis, okay? Now I can work out delta H. I can. I've got all the information that I need to, but I'm going to pull a bit of a calculus trick. Because we're dealing here with deltas, we're dealing here with very, very tiny things, okay? You can approximate when you're dealing with very small things in the same way that to develop the derivatives for sine, cos, and tan, we took advantage of this. For small values of x, right? Do you remember that? We needed this limit, this kind of limiting behavior to do all of the first principle stuff, right? I'm going to do exactly the same thing here. Delta h, right? This distance is actually quite awkward to get, but a distance that's easy to get is this chord AB. Have a look at that chord AB. How would I work out that distance? I could do the distance formula. There's an even easier way. The distance formula is built on Pythagoras, is it not? It's built on Pythagoras, okay? So that means that between every pair of points that you're interested in the distance, there is a little right angled triangle, yes? But the way we got A and B was to define the sides of that little triangle, right? It's little because the x thing is a little bit of x, delta x, and the y part is a little bit of y, delta y. Okay? Are you staying with me? Are you on track? Yes? Okay, so what I'm going to say is, I can continue, get rid of this sine x, 10x plus. I worked out r before. Now I'm on the trail of working out delta h. Okay? So I'm going to say delta h, well, it's not exactly equal to, but on these tiny, tiny scales, it is close enough to AB that I can work with it. Okay, as delta H gets smaller, AB will get smaller in exactly the same way. Like imagine delta H moving about, and it's always going to correspond to AB and be roughly the same. Okay, it's approximately equal to AB, but I'm just going to use Pythagoras to work out what AB is, right? What's the side lengths rather, of that right angle triangle? Wait, what? Delta? Yeah, I thought I heard a crazy word I wasn't expecting. Delta X is one of the shorter sides, and delta Y is one of the other ones. Okay. Now, again, I'm going to pull another trick, which maybe, honestly, I know the first time I looked at this, I was not that comfortable with it. I want you to notice that even though it's not exactly so, this little right angle triangle here has to exist inside of this big right angle triangle here. Do you see that? Like imagine the biggest AB you could. The biggest AB you could. It's going to be the original chord. Do you agree with that? Right. And as AB gets smaller and smaller, it's still going to be patterned after this big version. This will be AOB, would be the name of that triangle, right? But the thing about AOB is what kind of triangle is it? It's not just right angled. It's also isosceles. It's also isosceles. Now this triangle is not isosceles. But, I don't need it to be exactly isosceles. I only need it to be close enough. When delta X gets small, what's going to happen to delta Y?
It's going to become small.
It will also become small. So therefore, because I'm in this approximate infinitesimal world, I can say that this is delta X squared and another delta X squared. Now, I'm doing this not just because it's simpler. Why am I getting delta H in the first place? What is this going to be useful for?
Height of the
This is the height of this cylinder, right? It's not an annulus in this case because there's no hole in the middle. But eventually I'm going to add up a whole bunch of these, and then I'm going to integrate, right? I want to integrate with respect to a single variable because I don't know how else to integrate, yeah? So wherever I see multiple variables, I want to get away from them. I'm eventually going to get away from this one as well, but I'm not ready for that yet. Okay? Can we tidy this up? What are we going to get out of this?
delta X square root of root.
I can take out a factor of the square root of delta X squared, which is delta X. Don't need to worry about the absolute value because of course delta X is positive. And then you've got a root 2 hanging in there. Do you see that?
You need to justify it.
Not really. Okay. Not really. This is one of those extension 2 case by inspection type questions, right? There's so many other things going on in this question, I'm not going to worry about it. Okay, now, do you see? This was hugely important, right? Do you remember when we started and we were like, uh-oh, it's not on this axis, it's not on that axis, but now I have a relationship between the axis I am rotating around and an axis I can integrate on, right? Does that make sense? So this is really, really good. I'm pretty much ready to assemble my pieces now. I can actually do this, okay? I'm going to get rid of this guy, because I don't need it anymore. I want to make a statement like this, right? Limiting behavior, sum of a whole bunch of things, but I want to make it for what I now know to be the case.